this video, we're going to look at truth tables for our conditional statements, which are our if-then statements, and for our if and only if statements, which are our biconditional statements. Again, when we think about these statements, we have the parts of the compound statement which have truth values, but then we also have what makes these kinds of compound statements true and what makes these kinds of compound statements false. And so that's what we're going to investigate. So we're going to start off by doing a little investigation to figure out under what conditions will the statement if P then Q will be false. Okay, so just a little aside, in the book and in the lessons, sometimes they say P implies Q. I won't say that because when I learned symbolic logic, this was a completely different type of statement. And so I always treated this as if P then Q. But if you say P implies Q, they're treating these two things like they are the same. Okay, and I might slip and say P implies Q sometimes, but just so you know. All right, so we're going to consider an election where candidate A makes the claim, if I'm elected, then I will lower taxes. So P is the hypothesis antecedent that the candidate A is elected, and Q is the conclusion, the consequent, candidate A lowers taxes. So the statement, if P then Q, is false when candidate A lies. So what we're going to do is we're going to determine in each of these scenarios here whether P and Q are true or false, and we're going to determine if P then Q is true or false. We're going to determine, did candidate A lie? If they lied, it's false. If they didn't lie, it's true. So candidate A is elected and taxes are lowered. So P would be true, Q would be true. Did they lie? No, they said, if I'm elected, then I will lower taxes. They got elected, they lowered taxes. So no, they didn't. So that means that they were telling the truth. Candidate A is elected and taxes are not lowered. So the statement that they were elected is true, but the consequent is false. Did they lie? Yeah, they lied. They said, if I'm elected, then I will lower taxes, and they did not lower taxes. So did they lie? Yes, they lied. So that makes this false. Candidate A is not elected and taxes are lowered. So the antecedent is false, but taxes are lowered is true. Did they lie? No, they didn't lie. They didn't get elected. So they had no responsibility for what happened with taxes. So they didn't lie. And the same thing here. If candidate A is not elected, so the antecedent is false, and taxes are not lowered, so the second part, the consequent, is false. Did that candidate lie? No, they didn't, because they had no control over what happened to the taxes because they weren't even elected. So this is a no. It won't let me type no. Okay, so this is true. So we can sum up the truth value of conditional statements by saying if P then Q is true in every case except when the hypothesis is true and the conclusion is false. That is the only time, and I'm going to circle that example in purple. This is the only time that conditional statement is considered false, is if a false conclusion comes from a true hypothesis. So for this first example, what we're going to do is we're going to read these statements and we're going to determine the truth value for each simple statement. So essentially we have two statements combined together in a conditional statement. We're going to write the compound statement symbolically, And then we're going to use the truth values to determine the truth value of the compound statement. So the truth values of these simple statements. So my simple statements are, we're going to call this one P. Jeb Bush is a director. Okay. He does not make movies is going to be our Q. Okay. If you wanted to, you could say he makes movies is Q, and then you could say he does not make movies is not Q, but I'm just going to make the whole he does not make movies our Q statement. So writing this symbolically, or first, we got to determine the truth value for each statement. Is Jeb Bush a director? No. That is false. He's a governor, or was a governor. He's not a governor anymore, but he was a governor. Then he does not make movies. Does Jeb Bush does not make movies? That is true. Okay. So we have P, if P, then Q. And this statement was false and this statement was true. And so therefore, we have a true conditional. Because if a true statement follows from a false hypothesis, then the whole conditional is true. Now let's look at the next one. If Martin Scorsese is a director, then he does not make movies. So our first statement is P. Martin Scorsese is a director. He does not make movies. That is going to be our Q. We have if P, then Q. Is Martin Scorsese a director? That is true. He does not make movies. That is false. So because we have a true hypothesis but a false, or a true antecedent and a false consequent, that makes this statement, this compound statement, false. I promise it'll get more clear the more you practice. For our next example, we're going to make truth tables for each statement. Now, when we have a conditional statement here, that's what we just discussed. We had that the only time this is false is if we started with a true hypothesis and ended up with a false conclusion. So in this example, my truth values for if P then Q would be true, false, true, true. Okay. If you have a false antecedent, a false hypothesis, but it doesn't matter what your conclusion is. You're starting off from something false. So those have to be true. It doesn't matter what happened afterwards if you start off with a false statement. But if I start off with a true statement and ended up with a false consequence, then that is when we have a false conditional statement. So now we're going to look at what's called the converse. Okay, the converse is when you switch them. So before it was if P then Q. Now we have if Q then P. So I still wrote my statements in the order of P and Q, but now I'm looking at them backwards. I'm looking at this one first and I'm looking at this one second. So I'm starting with true. I'm going to put a little star here. I'm starting with true and going to true. That is true. Starting with false. So it doesn't matter what this one is. If I'm starting with false, then this is true. Starting with true and then getting a false, that is when this is false. I'm starting with false, so it doesn't matter what this one is, so that is true. Okay, so this is my truth table for the converse. We're going to do the same thing for the inverse. If you look at the traditional conditional statement is if P, then Q. The inverse is if not P, then not Q. So what I've done is I've written my truth tables or truth values for P and I've written my truth values for Q, but now I need to do not P. So not P is going to be false, false, true, true, because it's just the opposite of what P was. And for not Q, I get false, true, false, true. Okay, so therefore, I'm looking at, and I'm going to circle these in orange, I'm looking at this one first, and then following up with the not Q. So I'm starting false and get a false consequence. consequent, that is true. Starting false here and get something true, that's totally fine. Starting with true and getting a false, that is when we have a false conditional. Starting true and ending up with a true consequent, that is true. So this is our truth table for the inverse, which is if not P, then not Q. And the last thing for the contrapositive. So if the converse switched them and the inverse negated them, the contrapositive does both. Okay. So again, let me address the not P and, the not Q. And I'm going to circle those in, let's do yellow this time. But the one that I'm starting with is the not Q, so I'm going to put a star over that one in yellow. And we end up getting starting false with a false consequent. That is fine. That is a true conditional. Starting true and ending up with a false. That is when we have a false conditional. If I start with a true or false statement, it doesn't matter what the consequent is. That'll be true. Starting with true and ending up with true. That is true. So look here. I'm out of colors. Here we go. The conditional statement here has the same truth value in the truth tables as the contrapositive. So if you remember before, we would say that those two things are equivalent. You remember this symbol? Okay, that's our equivalent in logic. Two equivalent statements have the same truth values as their final result in their truth table. Now, if I look at the converse's truth table is true, true, false, true. And that's the same as the inverse, true, true, false, true. So these two are equivalent. Here, I'll make the double arrow so it looks like I'm saying they're equivalent with just a really long arrow. Okay, so conditional statements are equivalent to their contrapositive. The inverse of a conditional statement is equivalent to the conditional's converse. And then we have that just written out. That if P, then Q is equivalent to not Q, then not P. And we have the converse is equivalent to the inverse. If Q, then P is equivalent to if not P, then not Q. All right, so now we're going to look at part 2, which is looking at our biconditional statements. So what we have to determine is under what conditions will the statement P if and only if Q be true. Here we have that P if and only if Q is true when both if P then Q is true and if Q then P is true. So we're going to summarize the results from the previous problem. For if P then Q, we had true, false, true, true. And then for if Q then P, we had true, true, false, true. So we're looking for the situation when both of those are, both of the truth values for this one and this one are true. So we have that right here and we have that right here. So that is when our biconditional is true. And then our other situations where P and Q is true then false or false then true, our biconditional will be false. So true, false, false, true is our final truth value or truth table for a biconditional statement. So we can state that the biconditional statement P if and only if Q is true only when the hypothesis and the conclusion have the same truth value. Because look here, if P is true and Q is true, then the biconditional is true. If P is false and Q is false, then the biconditional statement is true. It's only when they have different truth values that we get a false conclusion. So again, let's look at example 4. We are going to determine the truth value for each simple statement, write the compound statement symbolically, and then they use the truth values to determine the truth value of the compound statement. So Spike Lee is a director if and only if he makes movies. So Spike Lee is a director is our first statement. We'll call that P. He makes movies are going to be our Q. Spike Lee is a director. That is true. He does make movies, that is true. So if we have P, if and only if Q, based on this statement, that is a true statement. Okay? Because both of the simple statements have the same truth value. In the previous video for the truth tables with and statements and or statements, I gave you the sentences, Anna has 3 cats, which we know is true. And we have the statement, Anna owns a house, which I told you was false. So if you think about the if and only if statement, if I said, Anna has 3 cats, if and only if Anna owns a house, that is a false statement because I do own 3 cats. It wasn't conditional on me owning a house. And so that biconditional statement is clearly false. So for each of these statements, we're going to make the truth table. Again, I'm using the alternate method to make the truth tables. You could do the method that the book shows traditionally, whichever one makes most sense to you. But again, for a biconditional, it's only true if both of the simple statements have the same truth value. So for this one, we'd have true, false, false, true. That is our final result. Going down to the one below it, I've circled the columns that we're looking at. So we want to see the rows where they have the same truth value. So that's going to be here and here. So we have false, true, true, false for this one. That's our final result. Then we have not P if and only if Q. So we're looking for when they have the same. There we go. So we have false, true, true, false. And then for this last one, here we have same right here and the same right here. So that's true, false, false, true. So looking at these, we can determine that some of these statements are equivalent. This biconditional is equivalent to not P if and only if not Q. Then we have P if and only if not Q is equivalent to not P if and only if Q. Again, that's because they share the same truth value as their final answer that makes those equivalent statements. All right, so this example 6, I'm going to let you try on your own. If you have any questions, please let me know. Here we have 3 words, 2 of which we've seen before. Now, just a reminder that a self-contradiction before we said was a compound statement that is always false, and a tautology was a compound statement that is always true. We're just expanding that to acknowledge the fact that it could be a compound statement or a conditional statement. So, compound or conditional statement that is always false is a self-contradiction. Now remember, compound statements are and are or statements. Conditional statements are our if then or if and only if statements. A tautology is a compound statement that is always true. And again, an implication is just another word for a statement that's always true, but in this sense, we're talking about conditional statements. So if you have an implication, that means you have a conditional or biconditional statement that the truth values for the entire truth table are all true. For example 7, I'm only going to do 2 of these. We're going to determine what kind of statement it is, whether it's a negation, a conjunction, a disjunction, a conditional, or a biconditional. We're going to make a truth table for the statement, and we're going to determine if it's a self-contradiction, tautology, implication, or none of those. So the first one we have P, if P, then P or Q. So this is this is the consequent, this is the antecedent, this is a conditional statement. Okay, so what I'm going to do is I'm actually going to do the style of truth table that the book shows and uses most frequently. I'm going to do that while I pause, and then you can check your work as well. So you might want to pause now and then check your work. So for this first conditional, I did the truth values of P under P, the truth values of P under P, the truth values of Q under Q. Then I evaluated the OR in red, and then I compared the P truth values here with the red truth values for the OR statement here to determine the truth value in purple for this conditional statement. And if you notice, in purple, we have our final result, and they're all true. So this is an implication. It is a conditional statement that is always true. The second example, we have a conditional here and a negation here, but the overarching, I guess, operator, if you think about it like that, is a or statement, so it is a disjunction. And again, I'm going to pause and suggest you pause while I do the truth table. So what I did is I wrote the truth values for Q, P, and Q. Then for the negations of Q, I did that in green. Then I got the values for the conditional here in purple, and then I compared the purple and the green to evaluate that or statement. Now remember, an or statement is true if at least one of the values or statements, simple statements, are true. So in this case, we had true and false, which makes it true. We had true and true, which makes it true. True and false, which makes it true. And false and true, which makes it true. So this or statement here is always true. So we would call that a tautology. Okay, so try with the others as well on your own. If you have questions, please let me know.